In this work, we present a novel imitation learning approach for bimanual multi-peg insertion tasks in a contact-rich environment that can effectively leverage physical contacts, recover from, and adapt to a variety of disturbances. For example, the system can recover from failing to insert all pins on the first try by adjusting its motion at runtime, conditioned on the measured perturbation. In our approach, we combine multimodal sensor data acquired from a force torque sensor attached to each robot's wrist, visual object tracking, and robot joint states to learn a Bayesian interaction primitive. The learned model then infers the temporal and spatial progress of the insertion task in terms of a phase value. When misalignments or other external perturbations are detected, the phase estimation, together with the underlying admittance controller, are used to overcome obstructions. This allows the system to correct and even reverse the estimated task progress, resulting in multiple insertion attempts as shown below. In extensive simulated experiments, we demonstrate the feasibility of our method in a dual-peg scenario, showing that our approach is capable of completing insertion tasks with tight tolerances and despite the presence of intermediate perturbations that revert the overall motion by estimating task progress and utilizing an admittance controller to complete the insertion. To train the Bayesian interaction primitive, we collect 30 demonstrations in the real world by moving the bracket, either with a space mouse allowing for 6-dimensional manipulation or by utilizing kinesthetic teaching. In our user study, we show that kinesthetic teaching is preferred due to its intuitive maneuvering. However, data collected with the space mouse enables the usage of force torque sensor data during inference, since all measured disturbances can be attributed to interactions with the environment. In our final real-world experiments, we show that the system is able to successfully place the bracket on all 4 pegs with a 90% success rate when using force torque sensor data during inference. Using the additional modality provides a 20% improvement over relying on joint states and visual tracking alone, making the space mouse the preferred data collection device, despite being more challenging for the human demonstrators.